Let's now talk about the technical aspects of machine learning, or the history of that. Many parts. So before the computer age to today, basically it was statistics. Then the first phase of neural computation, the perceptron. Then the area of classical AI. Then neural computation 2, so multi-layer perceptron. Then phase E, mathematically well-founded models, and now we are in the age of neural computation 3, at least in the way I number it, and maybe AI 2. So before the computer age, so a serious mathematical analysis of data has been done in statistics. And it even started with something which is called Bayesian statistics. So Thomas Bayes was a cleric, and this work was studied after his death, because it was probably still dangerous at that time to talk about these things. It's about updating the degree of belief in a hypothesis based on observations. And maybe there's a first exposure on some technical things. So first, you make an a priori assumption. So this is sort of top-down about a hypothesis being true or false. And it could be anything. It could be like the probability that a given party wins the next election. And you're allowed to have a personal belief, a degree of belief in the truthfulness of this hypothesis. But it should be a number between 0 and 1. So 0 means you don't believe in it at all, and 1 means you're pretty certain, very certain. And in the next step, you make an observation. So this first term is called the prior. So now you make an observation, D, so D stands maybe for data, and so that's certain, you really observe something. And you make some model, you assume under the hypothesis that or the assumption that the hypothesis is true, what is the probability of observing the data, and under the assumption that the hypothesis is untrue, what is the probability of the data. And that's called likelihood. And then, and this was Bayes' contribution, you can calculate the a posteriori probability, so the belief after you observe the data. Sometimes it's called inverse probability, using Bayes' theorem. So it's called theorem because it can be derived by probability, by the axioms of probability. So the probability that the hypothesis is true after you observe the data is the product of the hypothesis before you observe the data times the probability of the data given the hypothesis divided by the probability of the data. And the last one is more or less a normalization constant. And so this permits you a form of learning, because you make an assumption about how much you believe in a hypothesis, and after you observe some data, you revisit your hypothesis. So the full detail was really developed by Laplace, so some people think it should be called Bayes-Laplace theorem or theory, because Bayes didn't really give much detail on how you should apply it, and Laplace really tied it then to statistics. So Bayes' rule is a theorem in mathematical probability theory, so there's no question that it's true. But this is probability, and the statistics is the application of probability to questions in the real world, and there are different opinions. And so the people who believe in that Bayes' theorem is the right way of doing it are sometimes called Bayesians, and the people who follow other routes are sometimes called frequentists or classical statistics. But it has a huge influence, and a lot of machine learning has a Bayesian underlying flavor, was based on Bayesian ideas. So, for example, Bayesian brain hypothesis assumes that the learning in your brain can be explained by Bayes' theorem. So here's an example. So it's about bronchitis. So the probability that you have bronchitis, given that the X-ray was positive, so they saw something on the X-ray, is the probability that you should see this finding given you have bronchitis times the probability that you have bronchitis before you did the exam divided by the evidence. So here's this is a concrete example how you apply it to a problem in the real world. The Bayesian statistics is based on the concept of subject probability. So in contrast to classical statistics, you can even make, or even required to make statements about the belief in something. So that's also why it was criticized, because if you make statements about your own belief, that doesn't sound very scientific. So that was the main criticism. So before I throw a coin, I believe this coin is a fair coin with 99%, or 0.99. Or I believe that the probability that party X wins the next election is 45%. So this is something a Bayesian can say, and a frequentist would say, no, we cannot make these statements because we don't have repeated experiments. But Cox, so he was a researcher, he has made up the theorem, and he has some complicated reasoning, and he showed that if you are willing to put numbers on your beliefs, and under some weak assumptions, you can treat these numbers as if they were probabilities. So this idea of saying even my belief is a probability value between 0 and 1 can be justified. So here's the reasoning. If a 1 corresponds to the belief that an event happens with certainty, and if a 0 corresponds to the belief that an event does not happen, and numbers in between correspond to degrees of certainty, then these numbers exactly behave as probabilities. Yeah, so of course, then there was a counter development, so paradigm change. And I must say also these people, when Bayes made this hypothesis, there was no computer, of course. And even when these guys were active, there was not much computing power. So you have to deal and to do something with little computing power. And a lot of stuff which comes out of Bayes' theory, in particular if you do also distributions and beliefs about parameters, can be quite involved, even today with today's computers. They rejected that. They wanted to get away of this prior belief in something, but they kept the likelihood. So Carl Pearson is now considered the founder of modern statistics, also called classical statistics or frequentist statistics. And he was really happy that he finds something he could objectively measure. So I felt like a buccaneer of Drake's Day, so like a pirate. I interpreted that sentence of Francis Galton to mean that there was a category broader than causation, namely correlation, of which causation was only the limit, and that this new conception of correlation brought psychology, anthropology, medicine, and psychology in large parts into the field of mathematical treatment. So this thing called correlation, he thought can be measured objectively, and we can build a whole theory on that. Another very important person here is Ronald Fisher, and he made a lot of important contributions to statistics. And Egon Pearson, I think the son of Carl Pearson, Neumann, also made important contributions, but they were also very arguable people. So particular Fisher, he really didn't like Bayesians, and he made it very clear that he is doing the right way of statistics. And even today, I mean, probably 80 or 90% of statisticians are doing this type of statistics. In statistics and machine learning, it's more balanced, I would think. So that was the early of the 20th century, and then first computers were developed around 1940, 1950, and people thought, hey, maybe these things can be intelligent. And then people thought, oh, maybe we should look also at the brain for understanding how intelligent machines might work. And so the first development is here by McCulloch and Pitts. So it was the first attempt to formalize brain functions as networks of simple computational nodes. And these neurons are called McCulloch-Pitts neurons, and they are still used in deep learning, more or less. So on the right side, you see the cell body, this round object. On the left side, you see the input from the dendrites, which connect to the previous axons by synaptic coupling. I think it's called sigma. And then if H, so the summation of the weighted inputs, is above a threshold, the neuron fires and produces an output. And so in this simple model, the output is either 1 or 0, firing or non-firing. So quite impressive. John von Neumann, who invented the von Neumann architecture, was also interested in how neurons or how the brain works. And he even wrote a book. It was published after his death, A Computer and the Brain. So he concluded that the brain operates in part digitally, in part analogically, but uses a peculiar statistical language unlike that employed in operation of man-made computers of the day. So McCulloch-Pitts developed sort of the first model of a neuron, but they didn't study learning. So then there was Hebb, who stated Hebb's theorem. Neurons that fire together wire together. So it was starting to get mathematical, the learning part. And then Wiener is an important name. He developed a field called cybernetics, where control and communication was sort of transported into learning. So the whole world, even the universe, could be seen as one big feedback system subject to the relentless advance of entropy, which subverts the exchange of messages that is essential to continued existence. So feedback and entropy are important terms in his world. I mean, it's generated a lot of excitement, but then people also didn't exactly know where to go from there. So I think the interest slowly faded after 1950 or 1960. But these are really important advances. So Marvin Minsky, he just died. was important, but so the really important guy is Frank Rosenblatt, and he developed a learning algorithm for the perceptron, for the simple Macaulay-Pitts neuron, and he even formulated a convergence proof. So if the problem can be separated, and we learn about this later, what this means, then the algorithm will find this bounding box, or this bounding, the bounding separating hyperplane. And it's this learning rate is still the basis for machine learning, for the multi-layer perceptron and deep learning even. Around the same time, Widrow and Hoff also developed a learning algorithm they called Adaline, adaptive linear element, which is the foundation of adaptive signal processing. So he's shown on the bottom. Rosenblatt is in the center. So it's sort of a neuron without the threshold. So the activation goes through the output. And it seemed there was a debate if, in particular, in terms of what should be funded, where should the money go, into this type of learning machines or into the evolving area of AI. And at least the story goes, who knows if it's completely true, is that Minsky and Papert wrote a book called The Perceptron, or Perceptrons, and they analyzed the computational power of one neuron. And of course, one neuron is not able to do much. I mean, it's able to do amazing things already, to be honest, but not everything. In particular, the exclusive OR problem cannot be solved, which we will discuss also later. And supposedly this book destroyed the interest of the funding agencies in learning machines and perceptron, and all the money went into classical AI or rule-based AI. Let's briefly talk about this phase from the 57 to 1980s. It's called classical AI. So the roots were really in philosophy. And we mentioned Frege and Russell and Whitehead and also Wittgenstein. And so they had the idea that knowledge can be formalized mathematically and based on axioms. You can prove new theorems, and this would be the key to intelligence, which is not completely crazy, the idea. And I mean, they wanted to go beyond humans, and humans are sort of able to do some logical thinking. Maybe if we increase the logical thinking, we will have amazing machines. Yeah, you can divide it into two areas: normative or prescriptive decision theory. So that's concerned with the best possible decisions, no matter what the hardware, software constraints are. So if you think about optimal reasoning or rational optimism, it would be logic, or rational optimal acting, and it would sometimes called agent theory. And in contrast, it's more the descriptive decision theory or positive, which is more related to human intelligence, understanding human thinking. It's called cognition. And if you act indistinguishable from humans, there's a famous Turing test. So if you pass the Turing test, it's not distinguishable if you're a human or a machine. So there's still these two motivations: the abstract mathematical rationalist view and the one that we should be not distinguishable from humans. The birth of AI is considered this workshop in Dartmouth, which is a college in New England in the US. And the guys there were really amazing. John MacArthur, who suggested the term AI to distinguish it from cybernetics. He's the inventor of the Lisp language. Marvin Minsky, we already learned about. He made a lot of important contributions, but he's not really a classical AI person, but also not a machine learning person. He has his own mind. Claude Shannon, inventor of information theory, Shannon entropy, these sort of things. Arthur Samuel, who developed the first self-learning program to learn a game called checkers, so it's Dame in German, using a form of reinforcement learning. And Solomonov, founder of algorithmic probability. John von Neumann was there, founder of game theory and many other things. Alan Newell, CMU, and Herbert Simon. Simon won the Nobel Prize. So they're representative of strong AI, that intelligence has nothing to do with the substrate, so you don't have to study the brain, it's more like a mathematical thing, and other people. So here I think I have some pictures here. And yeah, so the classical AI is distinguished into different phases. The early enthusiasm phase, unlimited expectations about the capabilities. Herbert Simon said, so who is Herbert Simon? Oh, left bottom, yeah. I don't want to shock you. We are now in the world of machines that think. In a visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. And predicate knowledge was central for their approach. McCarthy proposed to formalize complete human knowledge in form of a homogeneous formal representation, first order logic. But then, they took their mouth very full. So they also tried translation very early on, and there was some famous failures. So the spirit is willing, but the flesh is weak. Became the vodka is good, but the meat is rotten. And reasoning also didn't scale up. But one has to say, I mean, these were the first attempts, and they were really brave. But they are also completely convinced about their capabilities, and then other people were a little bit happy that maybe they were a bit took their mouth too full. Then people thought maybe reasoning is nice, but knowledge is maybe even more important. So they tried to what I called facts and also complex theorems, simple theorems, complex axioms, simple axioms. So facts and rules, and they did a lot of interviewing of experts to get the important information from experts, so the complex axioms. And there were some successes. One was Dendral to infer molecular structure from mass spectroscopy data, or Mycin is important, the first maybe medical expert system. And progress in natural language processing with Charniak and Schenk. And at some point it even seemed there was a significant impact on industry. So McDermott built a configuration system for computers. And there was some excitement in the early 80s, maybe mid-80s, maybe late 80s even, where people thought, this will have a huge impact, and a lot of companies formed their own AI groups. But then, at least 84, so that's when I got a little bit in this field. It was really a different field, but I had some friends who were in the fields. Many Silicon Valley startups failed, and so for me it would be the beginning of the what they call AI winter, which is essentially, in particular in the US, the funding quickly dried up. In other countries like Germany, I think it was more a smooth thing. They never put so much money in it, and then it continued to flow. And machine learning also was not considered very important in this phase. Only deductive inference is sound. No, we had heard this before in the philosophical discussion that induction, you can never be sure that there's not an exception. If machine learning, it was symbolic machine learning, essentially trying to learn these rules. Case-based reasoning came from this area. Decision tree learning, inductive logic programming. And so since AI was sort of considered a failure at the time, the interest in neural networks increased again. So this was around the mid-80s. Just when the AI winter happened, machine learning or neural networks came and increased in importance. Maybe the substrate, which means the brain, is irrelevant after all. Learning became in focus in opposition to rule-based approaches. Fascination brain. So maybe there are some simple operations and principles in the brain which we can also put into engineering solutions. Maybe intelligence can only be reached via learning. And the successes were quite significant. Of course, there was a lot of criticism from other people, but there were some significant advances and successes, and particularly if you consider it in comparison to other high-dimensional non-parametric statistical methods, they work really quite well. Okay, so maybe the starting point was John Hopfield, who was a physicist who made the connection between neural networks and certain physical systems. So it's called spin glasses, and he could develop so-called associative content addressable memories. He also could solve combinatorial optimization problems. Interestingly, in particular, this last aspect is coming back in the area of quantum computing, because some form of quantum computing, the problems which can be solved are very close to the Hopfield type of formulation of optimization problems. So if you D-Wave, for example, does that. So if you're interested in quantum computing, you might look into this again. And he made, this link to statistical physics, the spin glasses. There was also a good argument why this is an interesting approach. The neurons are nonlinear. They work in parallel. They are error tolerant. They have feedback. So this was a feedback system. And people knew at that time they have to go from linear systems to nonlinear systems, but they didn't really have good theories. And suddenly there was something which worked. It could be implemented as an optical computer. That's how I got into this field, because I was in optical computing in the mid-90s. No, late 90s. No, late 80s. And relationship to brain functioning. But at the end, Hopfield networks, at least now, maybe now in quantum computing, they're becoming really popular again. But the solutions were not technically really competitive. They couldn't do anything in practical applications which you couldn't do with other methods. Here are some other names of people who worked in this field. Taylor, or in Germany, Karl Steinbuch, James Anderson, Wilshire, Grossberg, Kohonen. And prior work and links to statistical physics, Caianello, Little, and Shaw. Shortly later, the Boltzmann machine was developed. So that was, Hinton is already there, the second author, Eckley, Hinton, Zinovsky. And they could do something, not just associative learning, but discriminative learning. So they could be trained to solve a certain task. We will learn about that later. And so there was a close connection to statistical physics. So they essentially modeled the statistics more truthfully than in the Hopfield networks. And that was sort of a breakthrough, and had some nice successes, but fortunately, bad for them. The next thing was the multilayer perceptron, which worked much better in practice. That was invented by Rumelhart, Hinton, and Williams. So Hinton again, multilayer perceptron, a robust, powerful tool for modeling high-dimensional nonlinear dependencies. Beyond the limitations of the perceptron, because we had many neurons, we could solve the classical exclusive OR problem. There was an application called NetTalk, where the MLP was used to train a system to translate text into spoken text or language, and at that time took maybe 3 days of training, but it was very impressive. The New York Times had an article about it, and it's really a nice tool for modeling high-dimensional problems. So it was a certain breakthrough in neural computation, and although there was a lot of people didn't like it because there was not a good mathematics behind it, some really important people also saw the huge potential, also in statistics, for example. So maybe since '88 there was a certain hype, learning instead of programming. Now we're talking about the same thing again. But then in the middle 1990s, the interest, I always think it's more around 2000, but anyway, the interest in neural networks sort of decreased. We didn't really have a lot of respect from the other fields. We did good models, but it was, never clear if the statisticians at the end would be smarter and have better models, better understanding of learning. The connection to neuroscience became less strong. So it looked like it's sort of fading a little bit. But then there was something to the rescue, which is nowadays called machine learning. And a lot of advances were made also on the theoretical side by studying statistical machine learning, by using Bayesian networks, graphical models, by developing the VC theory, kernel systems, Gaussian processes, infinite models. We will talk about this during the lecture. And these methods have a much better theoretical description and analysis possibilities than neural networks. And for a while, they were dominating. And I will, in a moment, talk about why they're replaced by deep learning. So support vector machine, you might have heard of, is a very important model which came out of this area. But also very important was that suddenly the field had the recognition of other fields. So machine learning suddenly, and particularly these type of methods were used in bioinformatics, in vision research, in natural language processing, in information retrieval search engines. So companies like Google early on used machine learning and these methods. So everybody felt great. And AI increasingly became machine learning. So it was hugely successful, I must say. But why aren't we doing this anymore? So by my perception around 2010, there was some sort of trend that there was too much theory. So people developed theorems, and it was not clear if they had any practical relevance. And there was little progress on the performance side, more on the theoretical side. And people in particular Hinton, Jeff Hinton, the same Hinton we talked about, he sort of started the revival. And he never liked these shallow things, so like kernel systems, support vector machine. Essentially, the input layer, one hidden layer, not even a hidden layer, and then the output. So it's a very simple, direct system. The good thing is it can be mathematically analyzed very well. And here are some other names. Jeff Hinton, Joshua Bengio, incredible person. They're all still active. Yann LeCun invented the convolutional neural networks. Andrew Ng from China, who works in California and Stanford, and Jürgen Schmidhuber, who was a student in Munich and now works has a lab in Switzerland. And it was not because everybody waited for it or thought, oh, this is fantastic, we all have to do it. It's because of the success. So some difficult benchmarks were improved by a factor of 10. And this is, typically you improve something by 1% or something, not by a factor of 10. So the success was amazing, absolutely amazing. And that's why people got back into being interested in neural networks and deep learning, which is neural networks with many, many more layers. And it dominates currently vision research, natural language processing. It was immediately in products, in speech recognition in smartphones. It was before most people have ever heard of deep learning. It was already in the technical solutions. It's used in face recognition, language translation. And the perceived AI revolution we are talking about now is based on the success of deep learning, without any question. So here are some things we are doing, learning how to do games like AlphaGo, translation, so if you ever want to play with an AI system, just use Google Translate, question answering, like IBM Watson, for example, face recognition, autonomous driving, speech recognition, drones and robots, and many, many more things. And convolutional deep learning, recurrent deep learning, reinforcement deep learning is the basis. And also the community is absolutely amazing. So I work with students, I have a lot of students, and they are part of this international community of deep learning. They read the papers, they download the code. So here's an example, even a couple of years old now, where a student of mine used convolutional deep learning, recurrent deep learning, reinforcement learning, integrated it into one system and learned this game. I spy with my little eye. I see something you don't see, or you see was du nicht siehst. So it's about deep learning. A lot of good reasons why this is important, and we will learn about it. More data, deeper models, new algorithms, computational power, and this amazing community. But of course, it's also about data, that you need a lot of data for training, labeled data sometimes, which is expensive. In industry, we're talking about big data. In healthcare, maybe patient profiles, and knowledge graphs for machine understanding of background knowledge. So deep learning, it's still, and it has been for a while, for even since the mid-80s, whatever works best mentality. So ResNet has been one of the leading systems for image analysis with hundreds of layers. Nobody can really understand why we need hundreds of layers. Also, it attracts incredible talents all over the world, which are eager to attack any problem of relevance. Some new trends are explainable AI, that you try to give some understanding how the AI system works. It's getting more and more important. There's a drive towards general AI, which is sort of human level AI, which can solve all the type of problems humans are good at. Personally, I believe understanding the cognitive side, so the brain side, is important because it's the existing system, and it also tells you what is doable and what might be extremely difficult, and maybe we shouldn't start first with these type of problems. AI ethics, you probably heard about privacy, sort of connected to big data. How about military applications? This is sort of the hype timeline. In recent years, so it started with big data. Now it's called digitalization, machine learning, deep learning, AI. So maybe some people argue we should have stopped with deep learning and machine learning, because by calling it AI, it brings in a lot of people who are not really machine learning people. Yeah, I mean, the impact in industry is expected to be huge, but of course, in some industries, it's faster than in other industries. For example, search engines, anything with vision, with internet business models, we find AI or machine learning everywhere. Other industries maybe need a little bit more time, not because they're dumb, because the business models are not necessarily there. So finally, some details on the lecture. So technical foundations of approaches which are in focus today. Applied mathematics is important. So if you love applied mathematics, this is the right field for you. And we need these technologies. So hopefully you have some background. I will introduce most of the things, but more maybe in a review fashion. So linear algebra, so vectors, matrices, tensors are important. I mean, the good thing is you learn that all the stuff you might have learned, and you had no idea why this is useful, suddenly becomes useful. Calculus is important. You need to be able to calculate derivatives, apply the chain rule. The good news is the computer is doing all this stuff for you. Optimization, you try to learning becomes an optimization problems, essentially. We don't have to do too much in optimization because, again, gradient descent is doing the work for you. Probability, Bayesian, and frequentist statistics, I think, are very important. Typically, experts agree on what should be done, but not why it needs to be done, and there are different theories behind it. Park's theory, VC theory, is very similar. Frequentist statistics, Bayesian statistics. So I present the path I find most useful. It's impossible to cover everything, but hopefully you have a basis then to learn whatever you need to learn. So here's a statement why you need these things. So machine learning is based on the minimization of a data-dependent cost function. So that's an optimization problem with respect to unknown model parameters. The cost function is derived using probabilistic assumptions. That's why you need probability. And the model performance is analyzed by statistical methods. That's why you need statistics. With quadratic loss function, solutions can be derived with methods from linear algebra by setting derivatives to zero. So you need linear algebra and calculus. So I always say we don't need extremely difficult things, but yeah, maybe. It's more complicated than difficult, that's the problem, because it's a lot of stuff. So here's some literature. Deep Learning is an interesting, good book, if you're interested in deep learning. People always like Andrew Ng's Coursera course, or Stanford course on machine learning and deep learning. The elements of statistical learning can be downloaded for free. It's View from Modern Statistics. Machine Learning, a Probabilistic Perspective, a book from Kevin Murphy is quite popular. Pattern Classification by Duda Hart. Bishop's book. If you are interested in a more general view, including AI, this book by Russell and Norvig is the standard and also highly recommended. Machine Learning by Tom Mitchell, unfortunately, is outdated, but some chapters are really excellent. If you're interested in VC theory, this book by Schwartz and Scheib David is highly recommended. Data mining, here's the standard in data mining from Hen and Kemper. Kernel methods, Shaw Taylor and Christiani. Reinforcement learning by Sutton and Bartow. Bayesian data analysis. So yeah, reinforcement learning, I think it's also freely available and there's a new edition, so that's highly recommended if you're interested in reinforcement learning. Here's some Bayesian data analysis book by Gellman and co-authors. Statistics, there's some good books from LMU authors, former LMU authors. Probability, cognitive neuroscience, with Gazaniga, I like a lot. But as you can see, there's no perfect book. And there's no book I completely can recommend. Maybe the book on deep learning is quite useful. It has a lot of stuff. So some of the online lectures are probably quite good. For example, Andrew Ng's ones. And then, of course, my lecture. So here is some background information on the lecture you find on the web. So the assistants here are Christian Frey and Danny Casamur. Here's we have to see how the lecture, how long it will be, not online, so offline lecturing, and how to organize the tutorials. There will be more instructions on the webpage soon. And so this is what we did last year, just to give you an impression about what's going on. Oh no, it's not. Anyway, you can find it on the web, what we did last year, to give you some impression. So I integrate more and more deep learning into the lecture. You want to be up to date, and there are really some very smart ideas in deep learning. Of course, there's another lecture on deep learning in the winter semester. So there's a little overlap, but also complementary information. And yeah, I hope you enjoy the lecture and you enjoy machine learning. And yeah, I cannot say I see you in the next lecture, but so the next lecture will be, and then everything will be more technical. And so this was sort of a soft introduction, a lot of background history and so on. And next time we'll start with the meat. We'll start with the perceptron. If you understand the perceptron, you will already understand a lot of the basic concepts we need in machine learning. So looking forward to interacting with you in the future.